Hi, Algebra 2 friends. We're in Chapter 8 looking at Section 8.7. Today we're going to talk about solving quadratic systems. And you remember the last time we talked about systems, we had systems of linear equations. I'll put a little thought bubble around this so we can know that this is a back in the day thought. You might have 2x plus 3y equals 5 and 4x minus 7y is equal to 17 or something like that. And you had to basically, you're looking for the xy coordinate or ordered pair that represents the solution to both of these equations and the place where both of these lines would intersect. Well, we're going to do the same thing, but this time we're talking about quadratic systems. And so the systems involve quadratic equations. Quadratic equations are also equations that will produce not just parabolas, but also equations that will produce circles, ellipses, and hyperbola. So we've got interesting shapes and we've got a lot to think about. So let's go ahead and try this first example, example 1. So we're going to solve the system of equations that's given below. For x squared minus 4y squared equals 9. If you don't know, I can tell that this is, I hope you can tell too, that this is going to be a hyperbola, so something like that. And this is a linear equation. So they could intersect in a variety of ways, right? They could not intersect at all. They could intersect like that in two spaces. They could intersect, I guess, in one space. So we have a variety of, or one place, we have a variety of things we need to look for. So sometimes my point in bringing that up is that we can have more than one answer. How are we going to do it? Well, the cool thing is that we're going to kind of bring all of our elements of mathematics that we've ever thought of together and solve this problem. The first step is usually going to be something around substitution. We don't really have an elimination exact method for problems like this, but sometimes you might be able to use your elimination skills as well. But since we're going to use substitution, I'm going to isolate this x in this linear equation. So 4y minus x equals 3 implies that negative x equals a negative 4y plus 3. And finally, we get that x is equal to 4y minus 3. So this is what x is equal to. I'm going to take that and plug it right into this equation. So watch this. I'm rewriting the equation with that substituted value in there. So instead of x squared, I have 4y minus 3 squared. Let me make that squared. Minus 4y squared is equal to 9. Now I got to do a little bit of work, but this is just a perfect square trinomial, and I can multiply those pretty fast. So that's going to be 16y squared minus 24y plus 9. If that didn't make sense to you, if you were not feeling comfortable with that, just FOIL it out. You can do that. Multiply 4y minus 3 times 4y minus 3. And then I'm going to subtract 4y squared and equals 9. All right, finishing this off, I'm going to join some like terms together. So I have 12y squared minus 24y. And if I move this over to the other side of the equal sign, or if I move this 9 over here, I end up with 0. So all of this is equal to 0. So I join these guys together. This is there, and you get that. And so now how do we solve this? So remember, we need to solve for x and y, but we are solving for y right here. And how do I solve for y when I have a quadratic? Well, the first thing I do is I do make sure that everything is set equal to 0, and I factor. So what I'm going to factor out is 12y. I'm looking for the greatest common factor. That's like the basics of factoring, right? So I found the GCF, which was 12y. I'm dividing that out of each term, and I'm left with 12y times y minus 2 is equal to 0. And you remember how we handled these. We said each of our factors equal to 0. When I do that, I get that here y is clearly equal to 0, and here y is equal to a positive 2. So that lets me know that my two answers, because now look, I can tell I have 2 since I got 2 values for y, my two answers will have a 0 as one of the y values and 2 as one of the y values. The next thing I need to do is figure out the corresponding x values. I'm going to choose the easiest equation I possibly can, which is this one, x equaling 4y minus 3. Any of these would do, but I feel like I'm going to choose the one that's already isolating x, so that helps me out. And I'm just going to substitute in my different values for y. So this first one I'm substituting in 0. So x is equal to 4 times 0 minus 3. X in this case is equal to negative 3. So one of the points where these guys intersect is at negative 3, 0. And finally, the last one, x is equal to 4 times 2 minus 3, and x is therefore equal to 8 minus 3, which is 5. And so now I have the 2 points. I am going to ask you to do me a favor. Take these two equations, put them right into Desmos, and see if we get these two answers. All right? Okay, let's keep going. Sometimes when dealing with problems like these, you can get all kinds of situations. No solution, one solution, two solutions, three solutions, and even four solutions. We just had one with two solutions, but it depends on what the shapes are that you're intersecting and just where they're located on the coordinate plane. So I just wanted you to get a vision of what are some of the things we'll be working with. So here in example 2, we have what's considered a quadratic system because both of the equations are quadratic equations. What I would do in this case is I would want to see if I can eliminate some of the squaredness. And I say that I'm going to do substitution, but what I'll do is I'll substitute x squared because x squared has no coefficient here except -1, and this x squared doesn't have a coefficient either. So what I'm going to do is do a substitution that we've seen done before, is I'm going to rewrite each of these equations so that I'm solving for just x squared, right? So x squared in this case is equal to 25 minus 4y squared. So I'll put that there. In this top equation, when we solve for x squared, we can bring the x squared over to the other side and move the y over to the next side. So we end up with x squared is equal to 13 minus y squared. Now that we have these two things that I've isolated, if x squared is equal to that, and if x squared is equal to this, in these two equations, then clearly these two guys have to be equal to one another. So to me, to bring them together, that implies that 13 minus y squared has to equal 25 minus 4y squared. And so now I like to get it so that I have my equation in one variable and I can handle this. So I'm going to move everything over to one side. So when I do that, I am going to add 4y squared to both sides. And I end up with 3y squared plus 13 is equal to 25. And I'm going to think about this. Let me think. What would be the best thing to do? Well, you know what? Since this is the only term, I'm actually going to isolate the y squared term instead of treating this like a quadratic where we factor, because this is the only variable term. So watch, I'm going to subtract 13 on both sides. When I do that, I'm left with 3y squared is equal to 12. Divide both sides by 3, and I get y squared is equal to 4. Clearly, y could be equal to plus or minus 2. So I've got my two values for y, and now I need to find my corresponding x values. And I can use any one of the equations I like. I'll use this first one just because x squared is equal to 13 minus y squared. X squared is what we're looking for. 13 minus y squared would be 13 minus 4. So x squared is equal to 9. If x squared is equal to 9, then x is equal to plus or minus 3. But here's the thing. So when y was equal to positive 2, I would get plus or minus 3. And even if I put negative 2, because I'd be squaring the y squared, I would still get a positive 4, 13 minus a positive 4, and I still get x is equal to plus or minus 3. So what this is telling me is that my answer has 4 intersection points. And those 4 intersection points come from the fact that when I put one value in for y, like let's say 2, I get two values for x. I get a positive 3 and a negative 3. Even if I were to plug in the same negative 2, I square it, I get a 4, I'm still getting two values for x, which is a positive 3 and a negative 3. So what this shows me is that this intersection has 4 different points. Plug it into Desmos, check it out, and see if we get these same points. Our final example of this section is a system of quadratic inequalities. Solve the system of inequalities by graphing. So we're going to be solving, and we're going to solve by graphing. And so you know what that means. We need to think about the corresponding equation that represents this situation. So even though this is y is less than x squared minus 2, we need to think about y equals x squared minus 2. I said less than, it's less than or equal to, my fault. And even though this is x squared plus y squared is less than 16, we need to consider the graph of x squared plus y squared is equal to 16. I'm hoping that you can see that this is a parabola and this is a circle just by looking at the equation. I'm going to take these guys and get it out of the way so I don't interfere with my graph. And now that I've done that, I'm going to graph what I can. So when I'm thinking about y is less than or equal to, I know that this will be a solid parabola because or equal to is involved. So I would have my graph at -2, and it goes out 1, up 1, out 2, up 1, 2, 3, 4. This would be the shape. If you don't feel comfortable with this method of graphing, which is totally okay, we could talk about a different way to approach it. So this is right here at, let's see, out 1, up 1, out 2, up 4. This should be up at 2. And then so our graph should open up like that. Now, this is a solid parabola again because we do include the equal to, but we are shading downward. And so I'm going to get my pen here and kind of indicate that shading downward. So this is that representation of that part of the system. Okay, so now I need to do the next one. So the circle is not included, but we want everything that is less than, in a sense, because x squared plus y squared is the circle, equaling to 16 would be circle, but oh no, I'm sorry, we want 16 to be greater than this value. So if 16 is greater than this value, that means we want everything inside of the circle. If we wanted the circle itself to be greater than 16, then that would mean we want everything outside of the circle. And so the circle is centered, this particular circle is centered at the origin because of the equation. We can see that. And so we're going to go up 4, 1, 2, 3, 4, down 4, 1, 2, 3, 4, to the left 4, and to the right 4. And now this is our circle. It's not the prettiest circle in the world. Let me see if I can give it a slightly better shape by moving this out. But you guys get where I'm going. And it's going to be a dotted line, okay? So we need to get a dotted line in here. And let's see if I can do it. There we go. Or a dotted circle, because the circle is not included. But we want to have everything inside. So I'm going to shade in here.